Let's go over it in the process that I'd like to see you follow when you do problems like this. And then when you do your online homework, you at least have a guide for what it should look like, and then whether or not you're getting the answer that's appropriate for the material in your specific online homework. So as a reminder, those numbers all change on the online homework. So here we have two objects, and they're balanced in this scenario. So we have one bar that weighs 1 kilogram and another bar that weighs 2 kilograms resting on the end. The top bar is half the distance of the bottom bar, and the fulcrum is at some distance d, and the problem is wondering what is that distance d? So this is a case of static equilibrium. The object is in non-rotational and non-translational behavior. So with static equilibrium, we're going to do a torque analysis. Looking at the net torque, keeping in mind that in static equilibrium, our net torque is equal to 0, and our net forces are equal to 0. And remember, sometimes we use both processes to figure out forces and to figure out information. Since we're looking for a distance, that leads us to thinking about torques, because torques matter. Where the torque has to do with the radius and has to do with where those forces are acting, and that might lead us to information about distance. So in order to do that, we have to draw an extended free body diagram. That, of course, requires we identify the object. So what object could we be looking at the rotation about? Well, it's this sort of unit. Really, that bottom object is what's rotating maybe about that pivot point. So our object is going to be mass 1. So we're going to draw extended free body diagram on mass 1. We're going to look at all the forces acting on that object. Well, we can assume in this problem, it's not stated otherwise, that these are uniformly distributed. So with a uniformly distributed object, we want to remember that the force of gravity acts at the geometric center. So if this is a 2 meter long object, we know that we have the force of gravity at that location, and it pulls straight down. We also have the top block pushing down, sitting on top of this bottom block. Now, where does its force act? Well, again, the force of gravity acting on this top block we model is acting at the geometric center, so it's going to be pushing down at that geometric center of the top block. That's where the force of gravity will act. If this is 1 meter, then the force of gravity of block 2, and should make that arrow a little bit bigger since it's twice the size, it should be twice the size, it's going to be off of that end by half the distance, so that's about half the distance. All right, what else is interacting with the object? Well, this fulcrum is interacting with the object. It's causing an upward force. This is a normal force, so we can call it the normal force. We can call it the force of the pivot or the fulcrum, whatever you want to call that force. All right, that's the third force acting on the object. Now, we are interested in this distance d, remember. We're going to look at the net torques about a pivot point. So where do we define that pivot point? Well, one of our strategies is to find it at a place that we don't know the value of the forces at. And we don't know, we know these two, we don't know this one. So one strategy is to define the pivot point at that location. All right, now we're going to keep in mind that this distance is distance d. So once we have all our forces identified, we will number them and then look at the net torque about that pivot point for each one of those forces. So torque for force 1 is force 1 times radius 1 times the sine of the angle. So let's look at our radii for each force and our angles. So the distance from the pivot point to the force is r1. We extend that radius, curl to the force. This becomes theta 1. The distance from the pivot point to the force is r2. We extend that radius, curl to the force. That becomes theta 2, and we don't have a radius for force 3. All right, so our torque, force 1, is m1g times the radius. What is that radius? Well, this is where we have to use a little bit of our orientation, our geometry. We know that this is distance d, and we know that the total distance is 2 meters. So This distance, I wish I had more colors. Let's use blue. This distance we know is, since it's acting at the geometric center, this is at 1 meter. The distance between the end, because this is 2, and half of that distance, of course, is 1. So this radius is d minus 1. Times the sine of the angle, that's 90 degrees, and it's going in the counterclockwise direction, so it's a positive 90 degrees. I'm going to pick up the pen. All right. So we're left with m1, which is 1, times g. I'm going to leave the g in there, and you'll see why in a minute, times d minus 1 times the sine of 90, which is a positive 1. So there is our, we end up with g times d minus 1. Actually, let's leave this because you all have different numbers for, let's leave everything in variable form. 1. And that 1 is half the total distance. All right, so torque number 2. Well, that's F2, R2, sine of theta 2. Oops, I forgot a 1 there. So that's m2 times g, it's the force of gravity. Now what is this distance? Well, we know that the distance between here and here was 1 meter, right? And that's half the length of the overall. Half of that distance, because it acts at the geometric center, well, that's 0.5 meters. Okay? If this is 0.5 meters and I want to the distance d, how do I relate to the distance d? Well, what's left is 1.5 meters. So the radius is that 1.5 minus my distance d. Okay? So I'm at a half because I'm half the distance of, this is 1 meter, and I'm acting at the geometric center, and that would be a half a meter, so that's a half a meter at the end, which makes this distance 1.5 meters, since I have a total meters, 2 meters. And if this is 1.5, the difference between these is 1.5 minus my distance d. Times the sine of the angle, now this is in the clockwise direction, so that is negative 90, and I end up with m2g times 1.5 minus d times negative 1. All right. Third force. Well, that is force 3, radius 3, sine of theta 3, and since our radius is 0, we know that torque is going to be 0. So the net torque, the sum of the torques, are equal to 0. That's going to be m1 times g times the distance minus 1. And that's positive. Minus, there's my negative, minus m2 g times 1.5 minus the distance, plus 0 equals 0. So now I have to do a little bit of algebra. If I take and move this to the other side, I'm going to do that up here. I end up with m1g times d minus 1 equals m2g times 1.5 minus d. Okay, so my 0 goes away. I bring m2g to the other side. My g's will cancel, and I'm left with m1 times d minus 1 equals m2 times 1.5 minus d. Now, m1 was equal to 1 kilogram, so I have d minus 1. m2 is equal to 2 times 1.5 minus d. And now it becomes algebra. So d minus 1, we'll just leave that over here for a moment. 2 times 1.5 is 3 minus 2d. I need to combine like terms, so I'm going to bring my 2d to this side, and I end up with 3d. I'm going to bring my 1 to this side, and I end up with 4, and d is equal to 4/3 meter. All right, so does that make sense? Should it be longer than 1 meter. Well, 1 meter would be if this were perfectly balanced and I have more mass over here. So yeah, I expect it to be a little bit more than 1 meter. All right, you have different numbers in your individual webworks, but this is the idea. It's really important to recognize what object that you're looking at, what forces are acting on that object and where they're acting and how they relate to the variable that we're interested in. But following that torque analysis, and it should guide you in the right direction. All right, good job.